So we have seen for the situation when sigma is known to us. The other case which is we have been studying is when sigma is unknown. So whenever sigma is unknown, we know that the t distribution comes into picture. So let me just import numpy as np, and from scipy dot stats import t distribution, because we are going to work with t over here. np.random.seed, let us take that as 0. True mu, that is the true population parameters, true mu is equal to 5.0, and we are going to generate a random sample of size 100, and the data sample variable would contain your np.random.normal. So true mu 2.0, that is what we have taken already. So we have not defined sigma, so let us take as sigma as 2, and sample size. Now we have to calculate the sample mean and the standard deviation, sample standard deviation. So for that we need to write sample underscore mean. For this we would use NumPy library's mean function. So here we would write data sample and sample underscore std, that is for standard deviation, np dot, we will use the std function for this. Data sample would be there, and we would also specify that the sample variance has to be calculated. For this we specify DDOF as 1. Next we are going to set the confidence level. So confidence level, let us keep it as 0.95. You can change it and see what will be the resultant. Now we will calculate the critical t value. So for calculating the critical t value, so alpha would be 1 minus of confidence level, and your t critical, from t we will write t dot ppf 1 minus alpha by 2, and degree of freedom would be n minus 1, that is sample size minus 1. So here we have, what we have done, we have specified the confidence level 0.95, so 95% confidence level is there, and your alpha is defined, that is we have calculated the significance level, and t critical value, this is the critical value, and this t dot ppf function is from your scipy's t distribution module that we have imported already. So this calculates the percent point function, or you can say it would be the inverse of the cumulative distribution function for the t distribution. Okay, so here we specify 1 minus alpha by 2, this is the first argument, and this calculates the desired percentile. Alpha by 2 means that you are considering half of the significance level on each tail, and this we have seen that this is n minus 1. Right, now you can calculate the margin of error, MOE. So this one would be t critical into the sample standard deviation, that is sample std, sigma s by root n, right? So s by root n, so let me use np dot square root, np dot sqrt of the sample size. Finally, we would calculate your confidence intervals. So CI, let me write CI. So CI would be sample mean minus MOE and sample mean plus MOE. Okay, so if I want to see what is the sample mean, so let me just write. So sample mean, what was the sample mean? That is 5.11. Original parameter was 5, and let us see what is the confidence interval in this case. So it is 4.717 to 5.521. Okay, so we have obtained an interval for your population parameter, that is population mean, when sigma is unknown, by using the t distribution as well. So earlier we saw the case when sigma is known, so we use the normal distribution in that case. So t dot p, instead of t dot percent point functions, we used, if you can recall here, we used norm.ppf from normal distribution. Since here we are using t, so we have written for t distribution, and then margin of error is calculated. You can give a proper command for printing, as we have done earlier also in this case, that print true population mean, sample mean and confidence interval. So here I have directly written. So now let us begin with the confidence interval for population variance. So confidence interval for population variance. So for this we are going to import numpy, and so numpy as np, and we are going to import from scipy.stats, import chi-square, because here, if you can recall, for variance we need chi-square distribution, and we will specify np.randomSeed as 0 over here. You can write any other non-negative integer. Now we will define your true population parameters. So let us consider that the true sigma that we have is 4, or so let me write, instead of sigma, let it be variance. It means sigma is 2 in this case. We are writing sigma square. Okay, variance, we are dealing with the variance. Now we are going to generate a random sample from your normal distribution. So sample size, let it be 100. Data underscore sample, again this would store random numbers generated from your normal distribution. So this one would be 5, mean 5, variance sigma 2, and sample size. Now you can calculate the sample variance. So sample variance, as we know, it would be np.var using numpy's this function, and we would write data underscore sample with the degrees of freedom as 1, specifying that we are calculating the sample variance and not the population variance. Then you would set the confidence level. Conf level, let me just write a short form. It is 0.95. Okay, so 95% confidence level is there. After specifying these things, we need the degrees of freedom. So degrees of freedom, so df. So you can keep on adding the comments as I've done here. So you can write for true population parameters. So maybe it is just to make you remember that what you did at that point of time and what is happening in this code. Since here we don't have sufficient time, so I'm not writing it everywhere. Sample size -1. So degree of freedom is specified. Now we have to calculate the critical chi-squared values. So here calculate the critical chi-squared values. So here first one would, alpha would be 1 minus of confidence level, conf level, let me just write it, and chi-square lower, it would be chi2.ppf alpha by 2 and degree of freedom would be this that we have specified. Similarly, you can write for your chi-square upper. So let me just write over here. So here it would be 1 minus of alpha by 2. So here first of all we have calculated the significance level for your confidence level that we have defined over here. So it would be 1 minus of confidence level. This now we will calculate your lower critical chi-squared value based on the significance level alpha by 2 and the degrees of freedom. This will determine the lower bound of the confidence interval for the population variance, and on the other side you will calculate the upper critical chi-squared value based on the confidence level. It would be 1 minus alpha by 2 and the degrees of freedom would be specified. Okay. Now we can calculate the confidence interval. For population variance. So let Ci be degree of freedom n minus 1 into the sample variance that we have calculated, sample var, divided by chi-square upper, right? You have chi-square values chi2 underscore upper, comma df into sample var divided by chi2 underscore lower. Okay, finally you would print it. So these are the steps that we have already performed in your theory, and now we are just implementing that. So let us see what will be the true population variance. So that we have taken as true var, I think, yes. So that was 4 for us. Now we want to print the sample variance. Sample variance because it is built around that. So sample variance is this, sample var. And next, finally, is your confidence interval. So true population variance was 4, sample variance came out as 4.10, and confidence interval is 3.16 to 5.58 with your confidence level of 0.95. So now with 95% confidence level, we are proposing this as the confidence interval for your population variance. So you can change these parameters and you would get different confidence intervals. Basically, this code over here demonstrates how to compute a confidence interval for the population variance using the chi-square distribution. Last but not the least, so we have seen till now your confidence interval for mean different cases, and we have also seen the impact of changing the sample sizes on the confidence interval length. Confidence interval for population variance is also done. Last one for this week is your confidence interval for population proportion. So again we will be importing different libraries from here. So first of all, import numpy as np, and from scipy.stats import norm. So now we would write np.random.seed 0 So what will be the true population proportion? Let us take that as true prop as 0.3. Next, we are going to generate a binary sample, that is zeros and ones, to represent a population proportion. So for this, the sample size, let it be 200, and the data sample would be np.random.choice. So here we are specifying 0, 1. Size would be your sample size. Okay. And P would be 1 minus true P. P is 1 minus true P to true P. Okay. Sorry, I have written true proportion. So let me just write true prop. Yeah. So basically here we are generating a random binary sample. So we use np.random.choice to randomly select values 0 and 1 for your sample. P parameter over here is used to specify the probabilities of each value. So in this case, we have set it between this, which means that you have a 70% chance of getting 0 and 30% chance of getting 1 based on the specified true population parameter. So now you have basically, with this in line, you have a sample with zeros and ones, and that you are going to use to estimate the true population parameter. Okay, so you have to now calculate the, so let me write, calculate the sample proportion. So for calculating the sample proportion, we will use np.mean, the data sample that you have obtained here, confidence level, we will set the confidence level, so confidence level would be 0.95. Your critical value, we will calculate the critical z value, because in binomial, you can recall, we use the normal distribution because of the approximation that we studied. Okay. So for calculating this, we need alpha. So alpha, we have seen that would be 1 minus of confidence level, and your z critical value would be norm.ppf 1 minus alpha by 2. So here again we are using this percent point function to calculate your z critical value. Once this is calculated, as you can recall from previous cases also, the next thing is to calculate the margin of error. Margin of error. So margin of error in this case would be z critical into, np dot square root sample prop into 1 minus p into 1 minus p, right? So sample prop into 1 minus sample prop, it's z alpha by 2 under square root of p into 1 minus p divided by the sample size. Once you have calculated this, you would calculate the confidence interval for the population proportion. So CI is sample prop minus your margin of error, and the other side it will be sample prop plus margin of error. Finally, you can now print what are the true population parameters. So let me first run this. If you want to give the print command, that also is fine, or if you directly want to see. So we have true proportion as, so let me just write true proportion over here, came out as 0.3. Let us see what was the sample proportion, 0.27, and let us see the confidence interval that we have now, 0.208 to 0.331. So this contains your true population with 95% confidence. So you can see that sample proportion, or if you just look at the point estimate, it is just going to give you a single value as the output. And as you change a single value in that sample, the sample proportion is going to get updated. Now, instead of that, if you give an interval and you say that we are like this % confident that it is going to be in this interval. Now, so you are given a range of values for the true population parameter to fall between these two. Okay, so instead of giving a single value, you have given an interval estimate for your population parameter. So this basically completes your week 11, and in the next week we are going to learn about 2 sample problems. We are going to see how to obtain confidence interval in that case, and we are also going to learn about the concept of bootstrapping. Thank you.